Hello guys, welcome back to our video series of modeling and simulation. We are going to start the unit 2, which is agent-based modeling and simulation. Compared to the other two methods, AB is recent, the oldest being system dynamics. System dynamics is the oldest. Now, let's introduce agent-based modeling is relatively new method compared to system dynamics and discrete event modeling. In fact, agent modeling was largely an academic topic until simulation practitioners began using it some 15 years ago, let's say 20 years ago, because I wrote this book. I think was 2016, or so let's say 25 years ago. So is when it became a serious topic it was triggered by a desire to gain deeper insight into systems that traditional modeling approaches don't capture. What do we call traditional system dynamics and discrete? For a long time, system dynamics and discrete event have been used, and then later after AB was introduced to gain deeper insight, understanding of system that system dynamics and discrete event were not capturing. So another element which triggered ABE was the use of AB was advances in modeling technology made possible by computer science such as object-oriented programming, UML, and state charts. Yeah. The rapid growth of CPU modeling and memory. Agent-based models are more demanding than system dynamics and discrete event model. Agent-based modeling offers another way to look at a system. You may not know how a system behaves, be able to identify its key variables and their dependencies, or recognize a process flow, but you may have insight into how the system object behave. If that's the case, you can start building your model by identifying the object. The object here are called the agent, and defining their behavior. Afterward, you may connect the agent you have created and allow them to interact or put them in an environment which has its own dynamic. The system global behavior emerges from many, sometimes tens, hundreds, thousands, or even million concurrent individual behavior. There is no standard language for agent-based modeling, and an agent-based model structure comes from graphical editors or scripts. There are many ways to specify an agent behavior. Frequently, agent has a notion of state, and its action and reaction depend on the state. Then behavior is best defined with state chart. Sometimes behavior is defined in rules executed upon special event. So here we are going to use, I say that with AB you don't really use diagramming, so I think that was wrong. I meant we don't use series diagramming. So here we're going to use state chart diagram, a diagram of UML. So UML has I think 14 diagrams, and one of them is the state chart diagram. The state chart diagram depicts the the behavior of an object, and it helps having additional information about the behavior of the object, and helps identify methods of an object. You know what are methods? You know uh, you know that an object has a state and a behavior. An object has a state and a behavior. A state is represented by the data members. Like if we have the object student, we have the reg number, the name, the date of birth, all this stuff. They represent what? They represent the state of the object. And then we also have the behavior. If it is a student, we have a behavior like register, or take exam, or graduate, stuff like that. So these are the behavior that an object can expose. If we have like an object like a bill can be recorded, a bill can be displayed, a bill can be printed, for example. So this is the behavior of a bill. So with object-oriented programming, AB really gained in popularity because AB shows a different object, the different agent of a system and how they interact. And the best way of like programming object of a system is to use object-oriented programming. Now with the advances we got in object-oriented programming, it is now possible to really depict the behavior of agent of a system and then program them. Let's continue. In many cases, the best way to capture the agent internal dynamics is to use system dynamics or discrete event approach, and then place a stock and flow diagram or a process flowchart inside an agent. Similarly, outside the dynamics of the environment where they live is often naturally modeled using traditional methods. It is why many agent models are multi-method model. Now, what do we mean here? With system dynamics, oh, I mean, it has become super big. Here, system dynamics here. With system dynamics, you use stock and flow diagram. With discrete event modeling, you use flowchart. But what we are saying here is that AB is a multi-method, so you can also make advantage of them, to try to depict the behavior of a specific agent if it is required to do so. But basically, what we use here are state state chart diagram. So we are going to cover state chart diagram at the end of this. So after this video, we are going to dedicate a video for state chart diagramming, and you guys are going to use a state chart in your lab too when you will design the model, the market model. Upon completion of these, what are the objectives? Upon completion of this unit, you should be able to understand what is agent-based modeling, to know in which situations to use AB, the use of AB is appropriate, model and simulate a scenario using AB technique and algorithm. Now, what are the key terms we use here? The key term is, the first one is obviously the term agent. Agent in an AB, in an agent-based model, may represent very diverse things: vehicles, unit of equipment, product, project, ideas, organization, investment, pieces of land, people in different roles, etc. What you should understand is that this term called agent, we are going to use it in the tree method. We are also going to use it in system dynamics. We are going to use it in discrete event, but they don't have the same meaning. Here in AB, everything is an agent because everything is an object. And you know that an object can be either physical or logical. An object can be tangible or intangible. Equipment is something tangible because it's hard. You can knock it. A project is intangible. You cannot touch a project. A product, might be tangible, like a phone, like a car, but a product might not also be tangible, like a software. Ideas are not tangible. Organization are not tangible. Investment are not tangible. A piece of land is tangible. People are tangible. So all these we call them agent. So object, all objects are all objects are agent, and these agents have a state and a behavior. It means they have data members, they have attribute, and then method, a behavior. So we have examples. Yeah. Yeah, so this one you can read them. Now, historical root of agent-based modeling. So agent-based modeling takes its roots from various disciplines like game theory, complex system, complex adaptive system, artificial intelligence, and so on. So these are the areas which historically influence agent-based modeling. So what is ABM now? A simulation modeling technique where a system is modeled as a collection of agents and the relationship between them. Agents individually assess its situation in the environment and make decisions on the basis of a set of rules. So anything, as you can see, any object, tangible or intangible, can be an agent. Now we have different type of agent. Agent can be mobile, autonomous, adaptive, reactive. It can be interface, can be goal-based, utility, info gathering. So let's try to understand, this type of agent, and we are going to take some example. So let's consider a traffic control system. We are in a traffic control simulation. We are simulating traffic control, and it has different agent. You know, it can have reactive agent like the police. They are reactive because they enforce the law. Policemen. You can have info gathering like media. They inform the public of the traffic and incident. This is info gathering agent. So the media play the role of info gathering. Autonomous. Autonomous means disruptors. Disruptors like the weather, the accident. So they are autonomous agent. Goal-based like city planners. Would like the least. They would like the least number of accidents and greatest amount of flow through parts. So that's their goal. Is why they are goal-based. We are going to explain this later. Adaptive, like for example, drivers are adaptive, may avoid roads that are known to be overcrowded. Utility, for example, the driver also are utility, would like to minimize driver time to use less resources. So you can see that an agent can be classified in different categories. An agent can be classified in different categories. Yeah. Now let us see in the diagram there, and let's try to take example. Mobile agent, they move. Anything that can move is a mobile agent, like a car, like us, human being, an animal, anything. Now autonomous, they run without continuous input. When you can run without continuous input, like they instruct you what to do, then you are not autonomous. Like us human beings, we are autonomous because there's no one pushing us, to do something. We are autonomous. We make our own decision, and then we adapt. So we don't want instruction. We don't want input from other agents. So they are autonomous. Yeah. Let's say interface. Require system user interface agent. Like a software is an example of an interface agent, because it has an interface which is a bridge between the user and the internal of the system. Info gathering. Does it collect, filter, classify information? So then it is info gathering, like the media. You see, like a sensor gathers data and then send it to actuators. Now Goal-based, goal-based, they don't care about the utility, but they want to achieve a certain goal. Like we have seen down there, we have seen city planners or policemen. Their goal is to 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 secure the the population. They are goal based. You know, utility agent, utility they care about the they care about the utility. Like a driver, you know, he has a goal, it's true, but he wants to minimize the resources like fuel. You see, so he will try to minimize fuel by taking the shortcut. You know, it will be totally crazy. Me, I'm staying in Kimirongo. If I want to reach town, it will be totally crazy to try to go through, let's say, Kibagawaga, and then reach Gisozi there where there is Bielka, and then go to Kinamba, and then go to town. That will be totally crazy doing that, unless the roads are, unless they are constrained, like roads are blocked. But if not, any driver will try to save his fuel. So this is an utility a reactive agent. So if you know it has if it has a set of solution path, it's a reactive. So reactive agent are, I like saying that they're the dumbest one. They just react, they don't think, they are robotic. So they know that okay, they have a set of solution. They know that we were told to do this, like a security guard, A security guard is someone they have told him to scan. He has no decision to make. They have told him to scan everyone who enters to check, like actually there's COVID. We have reactive agent everywhere. You should be to make sure that you wash your hand, you put alcohol in your hand or two. Adaptive agent, they are the most intelligent to me. Can it change its behavior based on the past experience? Adaptive one are the most intelligent agent. Reactive are the dumbest, but these one are the most intelligent because they can trick their behavior. They can learn. If you can react based on last experience, it means you are a learning system. You see? So intelligence has to do with that capacity to adapt. If you cannot adapt, then you are not intelligent. If you cannot learn from your past experience, then you cannot adapt. So people who are intelligent, I'm not only talking about intelligence in class. There are different types of intelligence. Those who did artificial intelligence with me, they are classified, into different categories. And no one should lie to you that you are not intelligent. You are intelligent at something. But when we talk about intelligence, some people, generally they assume that we are all the things that we are talking about, books. It has nothing to do with that. You can be intelligent, in sports. You can be intelligent, in art. You can be intelligent in music. You can have linguistic intelligence. There are some people who are not good in books, but when they talk, you listen. So here, reactive in a traffic control system, for example, we have reactive. We have seen this. These guys are reactive. They enforce law. They are dumb. They know that we have to enforce those. We don't care. Now, info gathering, media, for example, autonomous. The weather, you don't control it. They are autonomous. It rains when it wants. You don't control accident. They happen when they want. You You might accuse the devil, Satan, and so on, but you cannot explain how they happen. Goal-based, they have a goal to achieve and they care about utility. They don't care about utility. It can take them whatever it takes them, but they have to achieve their goal. Otherwise, they are utility. Utility, they don't care. I mean, they care about the resources. They would like to minimize the resources. Adaptive drivers, they adapt. You know, um, they adapt because they are intelligent. They can decide. For example, to change the road. Not only use the main road. They can, if there is a jam, they can change the road. So they can adapt. So they are intelligent. So these are example of agent. And as I told you, an agent can be classified in different categories. So common characteristics of agent. Agents are autonomous and self-directed. So they decide by themselves. There is no continuous input. They are self-directed. They decide of the course of action to take. Now they are social. Their social means their interaction, between agents, so they can communicate. They can exchange information. There is communication. They are adaptive, means they can adapt their behavior based on past experience. They are goal directed, so they try to achieve the goal or maximize objective. They are heterogeneous. They are different. They are different, heterogeneous. They are different. Now, example of agent-based system. Agent-based system, 1992. We had very basic systems. We had very basic systems. Let's go. Here we go. For example, you see, before 1992, AB was still very young discipline. We try to depict a low traffic, a traffic density. Here we have a low traffic density, and here we have a high traffic density. Like okay, this one is now in their movement. When agent move, generally agent move. So in their movement, there can be cohesion. Cohesion means they can be looking to reach the same point, or separation. They can try to move from a certain point and take different directions. So here cohesion means they're all they're all going to the same point. They're all targeting to reach the same point. And separation, they're moving from the same point and taking different direction. Alignment, like flocking, for example. If you see, like in water, you see here there's an alignment. You see fish moving in an alignment. So the align can also be for example, here we have cohesion here. have cohesion. These people, this is a simulation. For example, here we are in a cinema room, for example, and all this, there's a cohesion situation here. All these people here, they want to, you know, to get out. You know, they want to get out here. People become injured when they collide at a certain speed. As a consequence, leaving the room becomes difficult. You see, and here there's also cohesion. But we were, you know, with a column here. You know, this mitigates the collision. When you put this point here, you see, you can better control. You know, a column in the front of the door can avoid injuries. So this, you can simulate this, but we are in a cohesion situation, so they are all moving to the same point. Now here we have a mobile. We're in a traffic control. We're in a traffic control system. We have cars moving in all the direction. You know, here there's no cohesion. You know, but they can move into all the direction. You see, sometimes there's cohesion, sometimes there's separation, sometimes there's alignment. You see, so in a traffic control, we have all these, you know, movement. We have cohesion, separation, so on, alignment. Now, so what we're saying there are just examples of AB system. We're going to see more advanced AB system. In our lab, we're going to have an agent. We're going to implement an AB system for the spread of a contagious disease. Now, modern application of AB. So you can use AB in economics. You know that economic has high abstraction. AB also applies there. You have seen in the other graphic, AB has a quite, compared to the rest, AB has a huge area of application. So you can use in economics, you know, stock market, supply chain, consumer purchasing behavior, agent-based computational economics. You can use it in biology, medicine, tissue growth, modeling the immune system, spread of epidemics. Yeah, the spread of epidemics is what we are going to simulate in our lab. You can use that in social science also. You know, traffic situation simulation, crowd simulation, terrorism. You know, AB can also be used. Ecology, you know, physics. You know, physics are law. Yeah. Cell assembly of nano material. So you have huge area of application of AB. Structure of agent-based model. What is the structure of an agent-based model? It has a set of agents, their attribute and behavior. So agents are the object, you know, and the attribute are what characterize them, their states, and then their behavior. Now we have a set of relationship, you know, how they interact and the mode of interaction, you know, and we have an underlying topology of connectedness defines how and with whom agents interact. Also have the agent environment, how agents interact with the environment in addition to other agents. Agents in their system, they interact between them, but they also interact with the environment. You see here you have agent in this system, agent interact with their neighbors. This one will interact with this, but agent here they also interact with outside the system. So they interact with the environment. This is the environment. Now topology, interaction topology. So they can interact like this, like cellular automata. You have cells, and they interact, so they move north, west, east, south. They can have space where they can move into two dimension, or they can be a web like this, a network topology. So they can interact like this, either cellular automata, either in a space, they have a space where they can freely move, or they can move and interact in a kind of network. Good. And then we have the lab 2, which is the market model. Now in this book, it has different phases. It has 8 phases, but in this book we have only included phase 1. We have only included phase 1, which is creating the agent population. But in the book you will find the entire the entire 8 phases. Now to me, if you cover the first 3 phases, I will be good with that. I will be good with that. So it shows you 5 new step by step. So I don't need to be there. In the name model, enter the model name market. So it shows you step by step. Now in the website, in the software I gave you, when you have installed AnyLogic, there are also video tutorial. You can also make use of them to attend this lab. So it shows you click after click. So you have to try it yourself. It shows you click after click. So you guys, you try it yourself. So this is lab 2. In this lab 2, if you perform the first 3 phases, I will be good. I'll be good with it. I will be good. So phase 1 is still going on. Looks a bit long because my Zoom is huge, but it's not very huge. Here you can run the market simulation, and you see how you see how people enter the market. So this is a business simulation. So you are trying to understand how a product enters the market. So you simulate on 10,000 people, and then you generalize to the entire. For example, if you have a product, how does it enter the Rwandan market? So it can be important doing that before you engage your money. It can save your money, because what if you engage your money in a bad project and people don't like, then it will be very, very, unfortunate for you. Now, before we move to unit 3, which is system dynamics, we say that we are going to use state chart. We're going to use state chart in AB. So in the next video, we are going to cover state chart, so that when you build your AB simulation, you understand, what we are talking about. So guys, thank you for watching. So see you in the next video. Bye bye.